Good afternoon and welcome to the OSIRIS-REx Mission Science Briefing. OSIRIS-REx stands for Origins, Spectral Interpretation, Resource Identification, Security Regolith Explorer, and it's NASA's first sample asteroid return mission. And we'll start off with Christina Ricci from the OSIRIS-REx, Deputy Program Scientist at NASA headquarters in Washington. Jason Dorkin, the OSIRIS-REx Project Scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Daniela Della Justina, the OSIRIS-REx Lead Image Processing Scientist at the University of Arizona in Tucson. And we'll begin with Christina.
Thank you, Nancy. So in the mission briefing before this, you heard about the launch vehicle, the spacecraft, the mission objectives. You even got to hear about the weather. So here, what we're going to be talking about is the science. So I'm going to just start off with talking about why we chose Bennu as the target asteroid. Jason is going to talk about the sample and the analysis that will be done. And Danny is going to talk to us about the mapping that's going to occur. So let's go ahead and begin with talking about why Bennu. So the ultimate goal of the OSIRIS-REx mission is to collect a sample from an asteroid and bring it back to Earth. But why was Bennu chosen for this exciting endeavor? Well, the science team selected Bennu after carefully taking into account three critical factors: the accessibility of the asteroid, the size such that it enables proximity operations and sample collection, and the composition of that asteroid. So let's get into each one of these individually, and we'll start off with accessibility. Go ahead and start my first graphic. So we need an asteroid target that a spacecraft could fly to and then return to Earth within a few years' time. The closest asteroids to Earth are called near-Earth objects, and they come within 1.3 astronomical units of the Sun. For those who don't speak in astronomical units on a regular basis, 1 astronomical unit is the average distance between the Earth and the Sun. It's about 93 million miles. For a mission like OSIRIS-REx, the most accessible asteroids for a spacecraft to reach are located between 0.8 and 1.6 AU. The ideal asteroid destination also has an Earth-like orbit, one that is fairly circular and low in inclination, so it's in a similar plane to ours. Bennu orbits between 0.9 and 1.36 AU. It orbits the Sun every 1.2 years, and it passes by Earth every 6 years, with an inclination that's only 6 degrees different than ours. So it really is optimal for accessibility for the spacecraft to go to and then return from. The next criteria for selection was finding an asteroid that was the right size to enable two critical portions of the mission: the proximity operations close to the asteroid and the actual collection of the sample. And go ahead and start my next graphic. Asteroids with small diameters rotate more rapidly than those with large diameters. For an asteroid that has a smaller diameter than 200 meters, it can rotate rapidly enough that some of the material on the surface will be ejected. Furthermore, it's difficult to match the rotation speed of a rapidly rotating object. So we need an object that's at least 200 meters in diameter. Bennu is actually 492 meters in diameter at its equatorial bulge, and its rotation speed is only 4.3 hours. So we'll be able to match the rotation speed of it and do a safe, smooth, slow high five to collect that sample that we will then return to Earth. The final criteria that made Bennu the choice destination asteroid for us was its composition. And go ahead and start my third graphic. Asteroids are categorized into different types based on their observed chemical composition. In the visible and infrared light, minerals have unique signatures, somewhat like fingerprints. Depending upon the features observed, scientists are able to identify various organic materials. The most primitive asteroids are carbon-rich and are believed to have material preserved from about 4.5 billion years ago, around the formation of our solar system. These asteroids could contain organic molecules, volatiles, and amino acids that may have been the precursors to life on Earth or elsewhere within our solar system. Telescopic measurements suggest that Bennu's surface is rich in carbon. Thanks to extensive measurements in the visible and infrared, as well as in the radar, which is what this map of Bennu was made off of, Bennu is the best understood near-Earth asteroid that has not been visited by a spacecraft. And with the return to Earth of these pristine samples with a known geologic context, we will enable precise analyses that simply cannot be duplicated by space-based observations or with studying meteorites. So Bennu's size, primitive and carbon-rich composition, and orbit make it one of the most fascinating and accessible asteroids. And that is why it was ultimately chosen as the target asteroid for the OSIRIS-REx mission. So Jason is now going to talk about the actual sample and what we're going to be bringing back.
Thank you. OSIRIS-REx brings back a large bounty of sample of the early solar system. Can I have the first graphic, please? So you have heard about how Bennu is a fantastic target asteroid. In turn, we have a purpose-built, fantastic spacecraft. The crux of OSIRIS-REx is origins, the search for the origin of the solar system and of life itself. And for that, it's all about the sample. Meticulous testing and cleaning are necessary to collect and return a pristine sample with a well-understood, well-characterized spacecraft from a well-understood, well-characterized asteroid. The design of the OSIRIS-REx spacecraft, instruments, and operations all serve to return this organic-rich sample safely with geologic context with the rest of Bennu. Then allow comparisons with other asteroids and with meteorites. After months of characterization and rehearsals, the OSIRIS-REx spacecraft autonomously descends to safely collect at least 60 grams, as much as 2 kilograms of surface stones and dust. This is a huge bounty. After the sample is collected, it is locked in the sample return capsule until the spacecraft delivers it to Earth in 2023. To keep this precious sample safe, there are no other science operations after the sample is stowed. And this will allow us to make sure that the sample is safe and that the spacecraft is safe by not interjecting other possible risks. The formation of the solar system was a violent but dimly recorded time. Although most of the record of the ancient Earth is lost to the dynamic geology that shaped our planet, there are lines of evidence that indicate that heavy bombardment by debris from the formation of the solar system around the same time helped form the oceans, and then a few hundred million years later, life. The detailed chemistry of what was on and delivered to the Earth and Mars, Europa, or Enceladus cannot be found in Earth rocks. This history is recorded in the minerals, compounds, and isotopes from meteorites and their parent asteroids. But meteorites land on the ground, and we never know where they come from. Furthermore, organic-rich meteorites quickly become contaminated with the compounds of life. These compounds are most important to understand our origins of meteorites and can only be understood by careful and tedious laboratory work, if at all. To maximize the sample of our samples on Bennu, we have a very clean spacecraft and a detailed record of the materials used to process to make it. This equips scientists who study the samples with the tools to directly verify what was discovered in Bennu's rocks and not accidentally carried from Earth. A scientist in my laboratory, Dr. Jamie Elsula, recently led a team to analyze some Apollo samples to learn the origin of their amino acids. She was not yet born when the sample was collected, used instruments not yet invented, and answered questions beyond the reach of science at the time. OSIRIS-REx, like the Stardust mission before us, will answer questions unanticipated at the time of launch, even questions we didn't design the OSIRIS-REx to answer. Just as we've learned from the Stardust Comet sample return mission before us, and Hayabusa and Hayabusa 2 missions on how to rendezvous with the comet, collect and return samples to Earth, we've learned from Near and Rosetta about how to maneuver around a small body. Samples of Bennu will be studied by science instruments too large, too power-hungry, or too delicate in laboratories around the world. We will dissect the sample to the atomic level to better understand the origin of the solar system and our place within it. The sample return capsule will enter the Earth's atmosphere to deliver precious fragments of the early solar system to the Utah desert in the morning of September 24th, 2023. Since 75% of the sample will be archived for scientists to request to study, perhaps you, your children, or your grandchildren will grow up to study the samples collected by the spacecraft we are launching now. Now, Danny will tell us more about how we choose the sample.
Thanks, Jason. So Bennu is going to be the first carbonaceous asteroid that NASA has had the opportunity to map the entire surface of. So this is very exciting. Can I get my first graphic, please? So mapping will begin by determining the shape of the asteroid, and understanding the shape of Bennu is of incredible importance so that we understand how to safely navigate around this body. Navigation will have some challenges because Bennu will be the smallest object that we've ever orbited a spacecraft around. One of the primary tools that we will use for mapping the asteroid will be the OSIRIS-REx camera suite, or OCAMs, a trio of cameras built by the University of Arizona. In conjunction with OCAMs, the 4 other instruments on the spacecraft will go ahead and map Bennu first globally, and then locally. By the end of our local mapping campaign, we will be able to see an object the size of a penny on the size of Bennu. Next graphic, please. So before sampling, mapping will take place over a year and a half to a 2-year period. And during this 2 years, the OSIRIS-REx spacecraft will be absolutely dedicated to finding the best place on the surface of Bennu to collect a sample from. This is pretty incredible because at the end of this 2-year period, scientists will know more about Bennu than we know about any other near-Earth asteroid. So we're collecting, again, an unprecedented data set. The mapping will take place globally so that we first can characterize and understand the major properties of this small world. And then we'll move along to a local mapping phase in order to evaluate the suitability of individual candidate sample sites. So the primary importance of mapping at Bennu is to find this great sample site and then subsequently go and collect a sample from it. But once we have a sample of Bennu, the maps will also provide critical context for that sample. Can I have my next graphic, please? So maps acquired during this 1.5 to 2-year period will place the sample into critical context. And the sample of Bennu that will get returned to Earth is at a minimum going to be 60 grams. So to get a visual for that, that's about 4 tablespoons of packed brown sugar. And because this represents a small portion of the overall asteroid, the maps that we collect and the remote sensing data that we collect at the asteroid are going to provide the vital link that we need to connect this sample into the global context for the world that is Bennu. So now that we've had a mission overview, talked about the sample and the mapping, back to you, Nancy.
Thank you, Daniela. So now we're ready to open the floor for questions. Please wait for the microphone and state your name and affiliation. Okay, right here. Right here in the striped shirt.
Hi, Bill Jellin from We Report Space. A question on the mapping. So the global mapping, if they determine through the Yarkovsky effect that eventually this thing would hit us, then we have an opportunity in 2135 when it passes between the Earth and the Moon to have a close approach. How will you save the maps? Will the global maps be transmitted back to us and saved in case we ever have to figure out the geography of Bennu in case we need to try and do something to divert it?
That's a great question. I mean, even security is one of the OSIRIS-REx mission objectives, but also from the spectral interpretation portion of our acronym, the data that we collect and then eventually build into maps for Bennu will be archived by NASA's planetary data system. And so NASA has a long history of ensuring that data is preserved and archived for future generations to examine, and this definitely includes the maps and all of the instrument data that will be collected by the spacecraft.
Okay, thank you. Right here in the front row.
I'm Jim Siegel. I'm with the Celebration News and Spaceflight Insider. I'm intrigued by the dust materials that you expect to find on the asteroid. For example, what makes you think there's dust there? What kind of evidence do you have or experience? And secondly, what would be the texture of this dust? Would this be like talcum powder or sugar or gravel or what?
So we have numerous lines of evidence that tell us the texture of the surface of Bennu, both from the thermal inertia, where you can look at the temperature of like a beach versus large stones, and the temperature changes from day to night quickly on smaller textures versus slowly with large textures, as well as using polarized radar from the Goldstone and Arecibo telescopes to give us a size bin of the surface of the rocks. We know that there are 1 centimeter sized stones, which is ideal for the TAG-SAM device to collect. And based on a reasonable size frequency distribution by looking at other asteroids, including Itokawa as visited by Hayabusa, we can understand how smaller and smaller pieces would break up into dust. And so we cannot see the dust from the Earth, but it almost cannot not be there. But the stones that we need, which are the high value samples, we have high confidence that they are present based on multiple lines of evidence.
Okay, right here.
Thanks, guys. Mike Wall from space.com. So I'm just wondering, would there be any advantages to trying to get more than one sample, or are you just going to get one sample and you're sure you've got it, then you're going to go because there would be more risks involved going back to try to get something else? So if you're sure you have one, I mean, could you just kind of talk about, are there any benefits to trying to get a second one if you could, or is that just getting too greedy?
So I'll go ahead and take that. So what we're going to do is, after we go out and do the slow 5-second high five maneuver with the nitrogen gas and collect the sample, we're going to actually maneuver away from the spacecraft so that we can rotate our spacecraft to measure the mass. Once we know we have 60 grams in there, we're going to stow and move away from the asteroid enough to where we feel that our spacecraft's in a safe position. Our priority is to bring back at least 60 grams of pristine material. So once we have that, we're not going to try to touch that again. We've got it. It's getting stowed. It's getting ready to come home.
Can I follow up?
Sure.
So as a scientist, I always want more. But the science team has been conditioned to understand how to minimize risk and have respect for engineering reality. And so I would love to have a spacecraft that is covered in sample return capsules. A friend of mine likes to say, Scott Sanford, who's on the mission, that if engineers designed a spacecraft, they would launch a bowling ball and get telemetry and declare mission success. If scientists designed missions, they would design a spacecraft that's too heavy with instruments to get off the pad. So coming up with a middle ground where we can ensure we get one high-value sample instead of risking it all and getting two is just not worth the chance. One is a lifetime of data anyway.
Great. Thank you. We're going to go to the phone lines, and we have Mark Gotch on the phone. Please state your question.
Thank you for this informative briefing this afternoon on this historical mission of OSIRIS-REx. Is going to be incredible. My questions are this. In using the TAG-SAM to take the sample from the carbon-rich asteroid Bennu, what will have to be seen or detected by the visible light cameras and spectrometer to indicate the exact place of the sample of regolith to be taken, and how far from the surface of Bennu will the sample location be able to be detected?
Okay, so I can take the first part of this question. So one of the instruments on the OSIRIS-REx spacecraft is called SAMCAM. And the purpose of SAMCAM is to watch the tag event and then later on to verify that there has been some sample collected by the TAG-SAM. So the TAG-SAM has, it's a ring, as we saw some of the images earlier, and there's a little bit of, you can think of it almost like steel Velcro at the edge of this annulus. And that will also interface with the surface of Bennu, and material will attach to it. So we will not only watch the sampling event, but we will also, at some distance away from Bennu, go ahead and turn the TAG-SAM so that we can look at it with SAMCAM and verify that we have acquired some material.
Okay, we're now going to take some questions from social media. Please, Aries.
Okay, thanks. This question is from @QuasarCam, and they want to know, what is the added value of retrieving the sample instead of analyzing it using onboard instruments?
NASA has a history of developing fantastic onboard instruments, such as the great instrument suite on the Curiosity rover on Mars right now. The problem is that those instruments, however fantastic they are, the design has to be fixed years before launch to minimize risk of change, and also to make sure that the instruments are light and robust to the launch environment, and that they don't need frequent tune-ups like laboratory instruments do. In the case when you bring a sample back to Earth, you can use laboratories the size of the spacecraft, even the size of buildings, like synchrotron facilities that were used to study the Stardust samples. And you can take rocks and slice them up into tiny, tiny fragments and put them into these beamlines and manipulate them using people that have the ability to adjust these objects in ways that robots can't, and then interrogate in ways in finer detail than you ever could. And of course, as we mentioned, people not yet born with ideas that we didn't have now can test them in ways that we couldn't even conceive of.
Yeah, just to follow on with that. So 60 grams is the smallest amount that we're intending on returning, but that's still going to be the largest sample return since the Apollo era. So this really is a sample return mission that's going to be the gift that keeps on giving. 25% of this sample will go towards the science team in order to fulfill their objectives. And then 75% is going to be stored in our curation facility at Johnson Space Flight Center in order to allow future generations of scientists to use instruments that haven't even been invented yet. So as Jason mentioned earlier, one of his colleagues at Goddard is still working on the Apollo samples now. So this sample return, OSIRIS-REx, is going to keep giving back to future and future generations of scientists. And it's really going to help us understand the solar system, so it's fantastic.
To the next question we had, which is, how could this mission have an impact on future missions, and which future missions?
Okay. So we're willing to share the answers here. So we're really actually going to be able to, the technologies that we have developed are going to help with several different types of missions to, say, small bodies in the future. The first of which is going to be doing those close proximity operations, being in that low gravity near the actual small body. Our mission has been specifically designed for that, and our type of research and design that we've done can be implemented towards future missions. The actual TAG-SAM arm, and then the sample return capsule, which was from Stardust previously, so we used a design that we know is tested and well validated and works. We will continue to keep using that design as we move forward. So it's really, the great thing about OSIRIS-REx is the instrumentation on board the spacecraft is at the forefront of technology. The sample return is at the forefront of technology. The fact that we're able to actually be in low gravity around this small body and still maneuver and operate is at the forefront of technology. So all of that from NASA is going to continue moving forward into more and more missions afterwards.
Okay, great. Right here in the front row, Ken Kramer.
Hi, Ken Kramer for Universe Today and the Northeast Astronomy Forum. I have a question for Jason and Christina. Jason, I think you mentioned after you collect the samples, you're not going to do any more science. No imaging. Is that why would that be?
We move to after we collect the samples, we move to a safe distance from the asteroid, and all the primary objectives have already been done. We've already thoroughly mapped and imaged and characterized the asteroid. It's all about keeping that precious sample safe, doing nothing that can possibly jeopardize it. We need to make sure that we can return the sample and not undergo any risk by getting closer to get better images. We already have everything we need. We need to show the same restraint that we have all along the program that's kept us on schedule and under budget to make sure that we don't grow our scope and do things that we don't really need to do, only what we have to do.
And that's for a few weeks or a few months?
It depends on exactly when we collect the sample. There's a window, but it could be several months.
Okay. For Christina, can you show with your asteroid model there, roughly how you'll be doing the sample collection with the spacecraft? What's the approach and
So I only have two
departure
hands, and one of them
trajectory?
has to hold the asteroid model.
Yeah, so right, it's probably a two-guy
Jason, start
operation.
rotating us. So basically what's going to happen is our spacecraft is going to go into the rotation period with it. And it's going to do lots of detailed mapping. And then eventually, when we feel safe and ready, we're going to lock in and we're going to come down and do a very safe, smooth high five. And then we're going to back away from the asteroid, make sure we have the mass we need, and then we are going to stow that once we have it. So stowed, ready for departure.
And do you think it is more likely from the equator or from another area?
You know, we're going to actually do detailed mapping of the entire surface of Bennu, as Danny described. And so what we're going to do is narrow that down to 12 different selection sites. I'm not going to say definitively where any of those sites are, because the great news is we have the instrumentation on board to be able to be definitive about that after we do the detailed mapping.
Hi, Jeff House, Space News. If you hit the jackpot with tag SAM, instead of getting that minimum 60 grams, you end up with several hundred grams. Do you change how you apportion the sample once you return it to Earth? Are you still going to set 75% aside, or will you set aside more or less of that for future study if you end up with much more than 60 grams?
Yeah, our agreement right now is for 25% for the science team and 75% for future generations. So, yeah. We also have is it 4% that's going
Correct.
to the Canadians? And 0.5% that's going to JAXA. We have an agreement with the Hayabusa 2 mission as well right now. So, yeah.
Okay, let's go back to social media.
Okay. And so now this question comes from CJ Steuben 9, and they want to know what instruments will be used to measure the Rokosky effect on Bennu and how.
Okay, so I can take this one. So we heard a little bit about the Yarkovsky effect in the last press briefing, and this is that small force that causes the orbit of the asteroid to change in a way that's difficult to predict. And this comes from sunlight basically turning the asteroid into something with small solar sails is a way to think about it. So we have two antennas on the spacecraft. We have a high gain and low gain antenna, and we will use those to track the position of the asteroid as we're flying in formation with it. And so any deviation, any small changes from what we anticipate the orbit of Bennu to be versus what we're tracking will be used to measure that small Yarkovsky effect.
Hi, Jared Hayworth for We Report Space. I had a question. What's the ultimate fate of the spacecraft after the sample return canister has been detached and sent home?
So the spacecraft goes into heliocentric orbit after the SRC goes to Earth and remains in orbit and could be a very healthy spacecraft, could be an asset should NASA wish to use that. But after that point, the OSIRIS-REx mission ceases operations with the spacecraft.
Okay, we're going to go to this side of the room.
Thanks. James Dean, Florida Today. A couple questions. First, I've heard first U.S. sampling mission. We've heard reference to Philae and Hayabusa, Apollo. I just wondered if you could, kind of put clearly in context how unique or rare of a mission of an event is this to not only, to touch an object like that and bring the sample home. And secondly, I was just wondering if, regarding whatever sample you get, I know you're carefully going to pick the right spot, but is there any outcome that could be kind of disappointing if it doesn't contain, certain compounds that you're hoping to find that would leave questions more open about origins, or is anything a good sample?
I'm going to quickly answer the second one, which is I think that anytime we get a surprise, it leads to more questions, and that's fantastic. As a scientist, you can't help but want to have more questions in the end. So one of the great things about exploring and about going to a really an unknown place is that you get to learn something new. So I think that we're fairly confident that we know this is going to it's a carbon-rich asteroid. We're fairly confident that there's going to be some of these organic compounds there, but until we get it back down to Earth, we won't have those definitive answers, and so we're looking forward to that. In terms of context with other missions, Jason, do you want to take that? Or?
Sure. So again, we have multiple lines of evidence that tell us this is a carbon-rich asteroid, but if it isn't, that means that we have to rewrite the textbooks on how we understand those lines of evidence, and that's exciting too. But as far as learning from other missions, we draw the spacecraft from the Juno and Maven heritage. We've learned a lot from NIRS encounters with asteroid Eros. We have exchanged information with JAXA on Hayabusa operations. We've exchanged team members with JAXA for Hayabusa 2 operations, and we work closely with ESA for Rosetta operations to learn how to operate around a small object, understand the thermal properties of asteroids, and try and get every piece of information we can to understand this strange environment and use as much engineering logic as we can from, as I said, these other missions, as well as, of course, Stardust, on how to bring a sample back from space.
Okay, right here.
Hi, Stacy Severin, Star Talk Radio. Just a question. We keep hearing about the carbon richness, and I wondered if there were any other objects that we know of that are as carbon rich that we might think of studying. Was it just the trajectory and the orbit of this that made it most attractive?
Okay.
So we heard earlier during the last press briefing about the small handful of objects that were suitable, both because they had favorable orbital characteristics, but also because these asteroids had the right composition, this carbon-rich material. So actually another great candidate was an object called JU3, and that is coincidentally the object that Hayabusa 2, the JAXA, Japanese Space Agency, that's become their target asteroid for sample return. So there are a small handful of objects in the solar system, and in fact in near-Earth space that did have the right characteristics, but ultimately Bennu was so well characterized that we wanted to go there because we already had enough data to help us start mitigating risk.
Okay, we're going to go back to the phone line. Mark Gotch, do you have a question?
Yes, Mark Gotch, Historical Aerospace News. Another question. Once the OSIRIS-REx mission has been launched, the rocket going forward, once the final stage is gone through and the spacecraft enters into space, the fairing has been shed, it going forward, what is the distance from the planet Earth to Bennu, and will it be traveling? It will be traveling on rocket fuel going forward on that distance. Can you also tell me how solar power will play into this mission?
I can answer some of those for you off the top of my head. So the majority of the push we get is from the launch vehicle, from the booster and from the Centaur. The Centaur gives us most of the push we need to get to Bennu. The Centaur itself goes into heliocentric orbit, becoming another pseudo-asteroid, if you wish. The spacecraft uses hydrazine monopropellant, and we undergo a deep space maneuver in January of next year, followed by the Earth Gravity Assist a year from now to put us in the same plane as Bennu. The solar arrays are used to power our electronics. It's not a solar electric spacecraft. So again, a monoprop, we have both the main thrusters and a large number of other thrusters for very fine maneuvering around such a small object. But we have plenty of power margin depending on where we are, either closer to the sun or further from the sun, because Bennu is on an elliptical orbit. Bennu is chasing the Earth right now and will soon catch up, but I don't recall the distance today.
I believe the total distance of this mission that it will have traveled is 4.5 billion miles. So it's got a ways to go, but we're really excited about that. Yeah.
Okay, we're going to take one more question from social media, and then we're going to wrap up.
Okay. This question is from at Cranaddy. And the question is, does NASA have a OSIRIS-REx twin, like the Mars rovers do? I think that question's for Jason, because I know we have a lab at Goddard.
I used to joke that ideally we would launch 2 identical spacecraft, one collect the sample and one be a blank, to do proper double-blind study when the sample comes back. That's really how to do the mission right, but no one would believe me, and that would drive our costs considerably. Like I said, scientists always want more. We built one spacecraft and we built it right. This is a PI-led cost cap mission, and we built within that cost, and there's not margin to build a second just-in-case spacecraft, no matter how much I want one.
Yeah, that being said, we're going to use the technology that was used here to develop further missions in the future. So we look forward to potential future missions. You know, NASA's still here, it's alive and strong, so we're going to keep on going.
Okay, right, great. Thank you, Christina, Jason, and Daniela. This concludes today's briefing. Thank you for joining us.